Hey AP Chem, welcome back to thermochemistry. Today we're going to talk about free energy. Welcome to free energy. So free energy is this weird thing in AP chemistry because it does have a concept, but we don't really use the concept of free energy at all. All we do is we use free energy as a calculation to indicate whether or not a reaction is spontaneous. So you can actually deal with free energy very, very functionally in AP chemistry without actually understanding the concept behind it at all. Now, with that said, I will explain the concept to you a little bit. But if the concept is like too abstract or weird or too simple of an explanation, you feel like that I didn't explain it completely, just know that you don't really need the explanation for what free energy conceptually is in AP chemistry at all. If you go into AP biology, you're going to deal with free energy actually a lot. You're going to deal with the chemistry or the concept of it a lot more in biology. So you can look forward to that. But for whatever it's worth, let me explain the concept of it a little bit to you after I deal with this hair that's driving me nuts. There we go. Okay, so free energy is exactly what it sounds like. It's basically the energy that's available to drive systems forward. In AP biology, it's explained as energy that can be harnessed in order to power a cycle. My very first explanation of what free energy is my favorite, not because it's the most functional, but because it's the funniest. It was, and that was a dead cow versus live cow. So, is the cow alive? Well, then you have a lot of potential energy that's walking around that field, right? But when the cow is dead, all of that potential energy now becomes available for other systems to use. You know, bacteria can harness the energy of the dead cow to power its metabolism. Same thing with fungus. Same thing actually with humans to some extent. So the cow itself is energy, whether it's alive or it's dead. It's just two different forms of energy, one that's a stored energy and one that's an available energy. Now, in a less morbid explanation, you can think of energy in a chemical sense in the same way also. Is your energy locked up inside a bond or inside a lattice? Or is that energy free and available to be harnessed for a cycle? You can think of like nitrogen and oxygen. When we have nitrogen and oxygen gas like floating around together, there's a lot of potential energy there. If you get those two things to react, they are going to react pretty violently, pretty exothermically to produce nitrogen monoxide probably, which is going to give off a lot of energy. However, when it's just nitrogen and oxygen gas by itself, that energy is not available. It's locked up in those bonds. And so those molecules slam into each other all the time without actually causing a reaction to occur. And so that would be considered potential energy. Once that energy is manipulated somehow, though, whether it's by a spark or by some other condition, which elevates the molecule to a point where it can then fall apart and make the energy of its bonds available to drive that reaction forward. Maybe an example that you're more familiar with would be like burning paper. Okay, we have paper, we have oxygen, and when you have the two in contact, no reaction is going to be happen until you do what? You light a match. But notice you just have to light a match once to start that paper on fire. You don't have to keep lighting a match and touching it against every single molecule in that piece of paper in order for the reaction to cycle forward, because once you use that match to break the bonds of carbon and hydrogen apart so that they are available to react with oxygen, then that reaction produces energy, which can be fueled to pull more carbon and hydrogen apart, which can then react with oxygen and produce more energy to pull carbon and hydrogen apart. So it's kind of like a chain reaction. If there is energy available to start the chain reaction, then the reaction itself will continue to provide the energy necessary in a free version, in an available form, to keep that chain reaction going forward. So that's kind of the concept of free energy, or at least it's part of the concept of free energy, or at least it's free energy as far as I understand it. If you look through your textbook and actually look through, I think I have 5 different chemistry textbooks that are all at our like AP college 101 through 103 level. Not one of them provides a conceptual explanation for free energy. So that's kind of what it is. Now let's talk about what the AP College Board cares about, and apparently every other college chemistry textbook out there cares about, is how free energy is used to predict spontaneity. So really, what we're going to do is we're going to calculate an answer for free energy, and we're going to look at the sign. And the sign of free energy is going to be able to tell us, is our reaction spontaneous or is our reaction non-spontaneous? And so this all comes down to this equation right here. So notice G is going to be free energy. H is enthalpy, T is temperature, S is entropy. Now, notice that G, H, and S don't have subscripts, right? Subscripts are lacking here. And so let's deal with what G, H, and S these actually are. So that you can use the correct ones, because you can't plug in any H. You can't plug in any S in order to calculate this out. So H is going to be delta H of the system, whether that system is a reaction or a neutralization or a formation or a physical change, doesn't matter. It's going to be delta H of the system. Delta S here is also of the system. So from this point on in our lives in chemistry, if you ever see a delta S with no subscript, it's going to be delta S of the system. And we kind of talked about a little bit about this yesterday. Why they do that is a little strange to us at this point in our life, because up till now in chapter 17, it certainly seems like delta S of the universe is the most important entropy that we've dealt with, because it can predict spontaneity, right? Well, delta S of the universe is extremely hard to actually measure or calculate because it's of the universe, right? And so delta S of the system actually becomes much more practical for us moving forward. And so you'll start to see that delta S of the system is actually a lot more functional. It's used a lot more, and actually it's in the free energy equation, which can be used to predict spontaneity too. And so delta S of the system from this point on kind of becomes the important entropy for us anyway. So that all goes to say, if you ever see entropy with no subscript, it is entropy of the system. Okay, so from this point on, I want to show you, before we kind of move on from here, you have seen the most important equation we are going to use when we are talking about free energy. However, free energy talks about spontaneity, and so does entropy of the universe. So I want to take a minute, go down a side path here, and show you how free energy and entropy of the universe are related. They are related. We can relate them in an equation, and that equation is going to show us the two signs for entropy of the universe and free energy, and how both of those signs are going to point towards spontaneity. So stay with me. We're going to derive this equation that you see at the bottom of your screen. And I want to show you how we get there. So if we start with this equation that we have at the top, and we try to get entropy by itself. So in order to do that, we need to divide this whole system by T. So it disappears out of this term, but it actually gets added to our other two terms. And that's what you're seeing right here. We're going to divide the whole equation by negative T, actually. It gets divided out of your entropy equation, but it actually gets added into your enthalpy and your free energy component. Okay, so now we know that, ignore this. This got spaced out super weird. Okay, we also know that delta S of the surroundings is equal to delta H over T, and there's a negative in that equation. Oops, there's a negative in that equation. Okay, so we know this was one of our equations from earlier. We've already talked about this equation. So what we can do is we have our equation manipulated here so that delta S of the system is by itself. We know that delta S of the system plus surroundings is equal to delta S of the universe. Okay, so if this term, see if my circling ability can get a little bit better. Okay, so if this term is equal to delta S of the surroundings, and this term is equal to delta S of the system, okay, delta S of the surroundings plus delta S of the system is equal to delta S of the universe. Okay, so delta S of the universe, this whole right side of the equation is delta S of the universe, and that is equal to the whole left side of the equation, which is equal to negative delta G over negative T. Okay, so this is how we get to our equation that relates delta G to delta S of the universe. So notice something here. If delta S of if the system is spontaneous, what is the sign of delta S of the universe? The sign of delta S of the universe is positive in a spontaneous system, right? So if this is equal to negative delta G over T, right? What sign does delta G have to be in order for this equation to come out to positive? Delta G must be negative in order for negative delta G over T to be equal to something positive. So if delta S of the universe is positive for a spontaneous system, that means delta G, or free energy, must be negative for a spontaneous system. So it's a little bit confusing because one is positive and one is negative for a spontaneous system, right? But this is why, because the equation that relates the two has a negative in it. So they couldn't be the same sign. If you had the same sign, let me show you what would happen mathematically. If delta S was positive, and delta G was also positive divided by a change in temperature, the equation wouldn't work. This side, which is negative, is not equal to this side, which is positive, right? It wouldn't work. So they can't be the same sign for a spontaneous system. They must be opposite signs for a spontaneous system. For a spontaneous system, delta S of the universe has to be positive, delta G must be negative. Okay, so that is a really important detail you need to know. Like I said multiple times in this unit, we live in die-off signs in this unit, hopefully more living than dying, right? So it might be worth making a table, summarizing your signs, doing your signs off the top of your head once a day. Maybe at the beginning of your homework session, just start with making a table and thinking through all the signs. Also might be worth putting a chart with the signs on your little page at the end of your notebook that is the to review the week before the test page, right? We only deal with thermodynamics here, and then it kind of pops up once in a while in a couple of the other chapters, but we really don't deal with it in depth again the rest of the year. But these signs are crucial, and the AP College Board tests them all the freaking time. So make sure you know these signs now. Make sure you know the signs walking into our test. Make sure you have practiced the signs multiple times before our test. Make sure you know the signs walking into the AP test in the spring too. Once you get the signs, once you're comfortable with the signs, this chapter becomes a joy. It becomes kind of like a puzzle, right? But you've got to work those signs out before you can kind of take that breath, relax, and really enjoy the material. Okay, so now that we know basics about delta G, let's look at how it's used. Okay, so let's look at a fairly basic system here. And that system is going to be solid water going to liquid water. So we have like an ice cube here, and the ice cube is going to be melting into little free-floating water molecules that are all mucking about, floating past each other. Okay, so they give you the delta H naught of the system. Remember that naught is going to mean standard temperature and pressure, and also 1 mole. They also give you delta S naught for the system. Remember that delta S naught is of the system. And they want you to find delta G at -10, 0, and 10. When is the system spontaneous? So go ahead, pause this video, work it out, see if you can get an answer for delta G at these 3 spots, and I'll do the same. Okay, so here we go. I have delta G for these three systems. The first one is going to be -10, the second one is going to be 0, and then the third one is going to be 10. So notice that the first one comes out positive. The second one comes out negative, but barely, and then the third one comes out negative with a pretty good magnitude. So system is not spontaneous at 10 degrees Celsius. System is barely spontaneous at 0 degrees Celsius. Remember, that does not talk about speed of reaction. So this is a good time to remind ourselves that spontaneity and speed say nothing about each other. The thermodynamic functions of enthalpy, entropy, and free energy say nothing about how fast a reaction will occur. Now it is negative. I don't know significant figure-wise if it's supposed to come out at negative or not. At 0 degrees Celsius, we might assume that delta G would be equal to 0. And if that were so, then the system would have no tendency to occur in either direction. The system would be in equilibrium. So it did come out as negative, which means it should be spontaneous at 0 degrees Celsius, as long as our significant figures aren't throwing us off in this equation. But also a good time to talk about if delta G comes out to be 0, that's really similar to delta S of the universe coming out as 0. And then in the third scenario, it comes out as negative also, which means that at 10 degrees Celsius, this system is spontaneous. And that makes sense, right? We should go back and see if that's a logical answer, if that kind of jives with what we see and what we can observe. So ice melting into water, when does this occur spontaneously? Well, it occurs above the freezing point of water, right? Which is 0 degrees Celsius. So at -10 degrees Celsius, no, we wouldn't expect this thing to be spontaneous, which is what we found through the calculations. At 10 degrees Celsius, yeah, we would expect this system to be spontaneous, which is what we verified through the calculations. So this is kind of how the thing works. We'll do this one together as a class. Okay, let's keep going here. So just a couple reminders: if delta S of the universe increases, if the change in entropy of the universe for a system increases, the reaction is spontaneous. We can use entropy of the universe to predict spontaneity. We can also use delta G to predict spontaneity, because the sign of delta G predicts the sign of entropy of the universe. Entropy of the surroundings is determined by heat flow, more so. And then entropy of the system is going to be determined more by the positional probability of the system. We have talked about positional probability a lot. Here is another example that you can think of positional probability. Just another example. If you want to think through this slide, just pause it here and read through this slide. It's a good example, but we have talked about these examples a lot at this point in time. So this is just a little bonus. Okay, does the entropy of this system increase, decrease, or neither? So this is more of what we practiced before. We're going from 9 molecules on the reactant side to 10 molecules of the product side. Positional probability is going to increase. You'll have more positions available with 10 molecules rather than 9. And so therefore the entropy is also going to increase. Okay, we've done a couple of these already. We'll do a couple of these together once we get back live. We'll do this as live practice. Okay, so a couple details here. Notice that we've been talking all along of like delta G and delta S, so change in enthalpy, change in free energy. And that's because absolute values can't be determined. You can't actually collect information to figure out what the enthalpy contained in a system is. Remember, enthalpy is heat flow, right? So what is the heat flow of something by itself? Well, that's not really a concept that makes a whole lot of sense. In order to have a heat flow, you have to have a change that occurs, right? And so enthalpy and free energy are always measured against something. A lot of times, what they're measured against, if I can find my pen again, is final and initial values. Right? They're usually measured against where it started, and then we can determine the change from there. But they always have to have a reference point. However, you can assign absolute entropy values. And this is the third law of thermodynamics. The reason we can assign absolute entropy values is because entropy automatically has a reference built in. And that is a perfect crystal at 0 Kelvin. So the theory is that at 0 degrees Kelvin, motion ceases. And a perfect crystal is going to have perfectly uniform distances, perfectly uniformed angles between all the molecules. It will have a cubic unit that repeats perfectly. And so if you have this perfect order along with no motion, then that would be our definition of zero entropy. Now, if you really want to, if you have a lot of time on your hands and you really want to dive deep into the abstractness, the wonderful abstract world of theoretical chemistry and physics, you should YouTube this. Oh, that was not a star. There we go. YouTube this, find a whole lot of videos that go like deep into the rabbit hole of theory, and you come up with some interesting predictions. And also a couple experiments of scientists that are trying to reach entropy, perfect zero entropy at 0 degrees Kelvin with a perfect crystal. So it's kind of interesting, definitely beyond the scope of our class. Not all of us have time for these kind of things, but if you do and you enjoy it, you should definitely dive into that rabbit hole. Okay, so this again, this perfect crystal idea, again, we can understand it best if we have some analogy. So if you have a number of coins, we'll leave that number up to your imagination and just say we have n number of coins. There's only one way to achieve all heads. So that would be your definition of order, having all heads. There's only one way to achieve that, but there's a whole bunch of ways to achieve not that, right? One way to achieve order, a whole bunch of ways to achieve disorder. Similarly, there's only one way to achieve a perfect crystal, like we talked about with like every particle at a perfect distance, every particle at a perfect angle, every unit of that crystal perfectly repeating in whatever order it has. So you have to have all these things in place in order to have no disorder. Okay, this idea of temperature being an indication of motion, again, shows up in our lives in chemistry. So again, we just solidify this bond between temperature and motion. As temperature increases, motion increases, disorder increases. As temperature decreases, motion decreases, disorder decreases. If you look at delta S values in the back of your book, it is good to note that those values are given at 298 Kelvin in 1 atmosphere. 298 Kelvin is 25 degrees Celsius in 1 atmosphere. Okay. If you loved Hess's Law, you are in luck because we are about to go through Hess's Law, basically, with entropy and also free energy. So both of these things are state functions. Entropy is a state function, free energy also a state function. And so you can calculate the total entropy of the reaction and the total free energy of the reaction very similarly to how we used Hess's Law to calculate the change in enthalpy of a reaction. So it's going to be the sum of all the entropy for the products multiplied by their respective moles or molar coefficients. And then you're going to subtract again all the reactants multiplied by their molar amounts or their coefficients. It's also extensive because you have to look at the sum, and you have to multiply by the amount of moles for each. So the amount matters. Again, the table is going to be given in terms of products. So that's why you need the negative. If you want to use it as a reactant, you have to flip the concept, flip the reaction, and that's going to flip the sign, and that equation flips the sign for you. All right, so for example, calculate delta S at 25 degrees Celsius for the following reaction. So really what we're going to do is take all the reactants and multiply them by their coefficients, which is how many moles of the reactants we need per 1 mole of the reaction. So NiS is 53, oxygen 205, and then we have the reactants on this side, SO2 248, NiO, that's what did I use that before? No, I didn't. Okay, we're good. Okay, so remember, products, the equation is the sum, that was a bad sum, the sum of S of the products multiplied by all their molar coefficients minus the sum of all the reactants multiplied by their molar coefficients. Okay, so all of the products are going to be positive according to the equation. All of the reactants are going to be negative according to the equation. So you either have to take products minus reactants, or again, you can just put a negative sign out here in front of all the reactants. Okay, let's do this. All right, and I got negative 149. That's going to be in joules per Kelvin because I multiplied off all the moles. I'm comparing that to this unit here. I multiplied off all the moles, so moles gets reduced out. I'm left with joules per Kelvin. Ta-da! Did you get that also? Again, hopefully you're familiar with Hess's law, and this is kind of an easy transition to just discover that Hess's law applies for entropy as well as enthalpy. Okay, delta G, when we're talking about free energy, it's going to be the similar idea. So basically, it's the change in free energy that will occur. So the change in that available energy to harness in these cyclical cycles that will occur if reactants in their standard states are converted or reacted into the products in their standard state. So that's delta G naught. Again, we're talking about a reaction here. And what we're comparing with that delta, what that delta is, again, it's products minus reactants, final minus initial, products minus reactants. We're going to talk about how to calculate delta G. We have a couple different ways of calculating delta G here in just a minute. Conceptually, though, why do we need to know delta G? Well, it helps us to compare the tendency of a reaction to occur. So this is another way of naming spontaneity. What is the tendency of the reaction to occur? Not how fast it reacts, but what is its tendency to occur at all, right? So magnitude in delta G actually matters. We've been talking about signs all this time, and we've kind of ignored the magnitude all this time. But one of the notes that you want to make for delta G is that the magnitude actually makes a difference. If it's more negative, so let's say like you get two delta Gs and one is -1 and one is -100, okay? The -100 is more negative. That has implications about equilibrium. It doesn't tell you how fast it's going to get to equilibrium. It just tells you how far to equilibrium it's going to go. So for example, if you have, flour and sugar and oil and eggs and chocolate chips, and you're going to make some chocolate chip cookies, right? If you have a perfect amount of ingredients, if you use up all your ingredients, so you have 0 ingredients left and you can make 100 cookies, that would be as far to the right of your equation that you can go. If you use up all your reactants and you have only products left, that would be completely to the right. But let's say your reaction stops in the middle for some reason and you have only made 50 cookies. That would be, we would consider that your equilibrium point, where your ingredients are being made into cookies, but cookies are turning back into ingredients somehow, right? That would be your dynamic equilibrium point. Well, that is less to the right. So if you can make 50 cookies before you hit equilibrium, that would be less to the right than if you can make 75 cookies before you hit equilibrium. 75 would be more to the right than 50 would. So if your delta G is -1, maybe you can make 50 cookies. If your delta G is higher than that, is more negative than that, like -100, you know you can make more than 50 cookies before you hit that dynamic equilibrium point. If you're going to make this comparison, however, you have to be careful. It has to be the same temperature and pressure. Temperature and pressure can screw with where your equilibrium lies and where your free energy values are going to lie. Now, this is an interesting concept because we get into this idea of equilibrium. When we get through the equilibrium chapter and we look at equilibrium in full depth and we look at equations to help us deal with equilibrium, we're going to revisit this idea of the relationship between free energy and equilibrium. So you'll notice in this chapter, we're actually skipping a section of practice problems in the book. We're skipping the practice problems that walk us through mathematically this relationship between free energy and equilibrium. We will come back and do these questions once we go through the equilibrium chapter. So this is kind of a preview of what that relationship is. Okay, if a delta G is more negative, your equation is going to go farther before it hits equilibrium. It's going to create more products before it hits equilibrium. And then we'll look at this mathematically once we understand equilibrium a little bit more. Okay, so here we are going to get into ways to calculate delta G. Now, we've kind of touched on a couple of these, but I want to make sure you understand that there are multiple different ways, and I want to walk through some practice with you for each of these multiple ways to calculate delta G. And so we're going to stop here for today. This is a good stopping point. And we will walk through these 3 different ways to calculate delta G on tomorrow's video. Okay, let me know if you have any questions. I'll see you in class.